Yeah. You guys can hear me okay, right? I hope.
Yeah.
Okay. I mean, I got a little microphone level. I must be getting old school or something. I never trust it. I like to hear that people can hear me. uh, I think this, yeah, this isn't too bad. I'd actually never done this way so far with everything online. I've either just been recording my ugly face with, you know, different computers, things like PowerPoints and Word documents and stuff like that, but I haven't done this yet. So this should be interesting. Oh, what the heck. Everybody wanted to come and do this. Now I see who my three go-getters are. Ray was in there. Oh, well, in any case, so we are recording. We are live. But so let's look. I guess this is kind of a practice problem. We'll kind of bring it all together, review for capacitors and capacitive reactances. Oh, there we go. And all that good stuff. I kind of laid out the three styles basically that we dealt with so far. You know, we know at this point, you guys are you able to see this okay? Does this come through? Yeah,
Yeah.
that doesn't look
It's
too.
upside down.
Is it upside down?
Yeah.
Shoot. All right. All right. Let me think here. Now you're gonna have me. Huh. Wonder how. So you're saying it has to be like that? Oh man, you just made my life horrible. Here, I was all proud of myself. I thought I had it. All right, let's see what I can. Hold on here. Oh boy, upside down. How am I gonna do that? The viewing on that'll be, and that's right side up.
Yep.
Really? That's so weird. It looks okay. I'll take your word for it. And that, can you view that okay? So far, right? It's just a blank sheet of paper. So, all right. Oh, there we go. Well, let's give this a shot then. Like it were. Oh, let me see if I can get my angle better. I don't know. Um, I guess I could do this. All right, let's give this a shot. It's kind of hokey. If I actually had to do this like on a regular basis, I would most definitely get me a regular video camera. I'll tell you right now. All right. So if we look at our very base, this is going to be crazy for me. our very base circuit, right? Where we just have a capacitor and an energy source. Okay. And I mean, you'll see these marked up different ways, like an E sub S or a B sub S or whatever. But suffice it to know, I mean, you see that symbol where it's got like a little, I mean, the sine wave is the key, right? You always have the AC energy source. And then over here we have a capacitor. Let's say, and I know we're going to get to the parallel ones. I just wanted to, I was actually kind of using it as a recap, if you will. So with this circuit, I mean, it's pretty much a no-brainer, right? What's the big thing I'm really going to have to look for here? I got to look for my X of C, right? So we plugged our formula in, we would know that X of C is equal to 1 over 2 pi FC. If we have a 1 microfarad capacitor, let's say this bad boy over here is 10 volts at like 100 hertz. And we pretty much have all of our unknowns at this point, right? So then just if we plug it in, 2 pi, we know that's 6.28 times 100 times the 1. Yeah, picking a 1 is like cheating. They're never that easy in real life. But yeah, if we did the map out on this and everything and plugged it in, we would see, well, we have 1 over the 628. Oh my goodness. And so, look at it. This is one of the bigger ones here. Hold on here. But anyway, so I just thought I'd get straight capacitive circuits. And of course, I mean, the angle of deflection on these, we know that with just a straight capacitor in there, that is going to be an exact 90 degrees. We know it's a negative 90. But the trouble comes in is when we start mixing them up, right? So we get like practice problems like this where we have the, oops, hold on. It's supposed to autofocus. I don't know about this thing sometimes. Zoom. Oh, God. Because honestly, I don't have an actual control on the focusing part of everything. Oh, come on. Yeah. This is not autofocusing. There we go. So this would be from the practice problems as well, and that's when we get a little more complicated. Excuse me. But I mean, basically, it's following our steps, right, at this point. So if we were to examine, let's at this point, if we looked at an RC series circuit, right? Capacitor in there. And we could say something like 25 volts, say 4 kilohertz. R over here is a 1K. C down here is a 0.02 microfarad, like so. So when you get a circuit like that, the first, I mean, pretty much in all of these when we're dealing with reactance, the very, very first thing we want to do is find out what our reactance is for our components. In this case, we have a capacitor, right? So what we want to find out is at this stage is what our very first thing is X of C. So we always plug it in, and the formula never ever changes. We always have it as 2 pi FC. So if we have our frequency and we have our capacitive value, we should be able to go ahead and find out what this value is. So 6.28, you know, 2 times pi. And we have about 4K frequency, and then we have a 0.02 micro as for our capacitive value. So the K and the micro come together and reduce that down, and the micro then become a milli value, you know, 10 to the negative third. So then really down below, what we would have happening is 6.28 is times 4 times 0.02 times 10 to the negative third. And then, yeah, I do. I don't know. I've always done the math the longhand. Sorry for my wife making a lot of noise. And I'm using Mr. Calculator. I can do so much, but after that, I'm no good. So essentially, if we did x of c, it would be like a 1 divided by 502. I believe. 1, 2, 3. Do that. And so basically, for this particular circuit, our x of c value, we'll call it like a 1.9K, and that is in ohms. So it's almost a 2K, and so a 2-to-1 ratio as far as our circuit is concerned here. And then basically we have a series circuit, right? So I'm going to have a couple of things I have to find out, and it's just like with everything else. I mean, we can do the phasor. If we have a phasor diagram, we can solve the impedance, okay? Because we know that these two components are on in different phases to each other, so they don't readily combine. So we would have to always basically draw out a phasor diagram to show what I need. In this case, the R is an X of C, right? And then to get a Z total here. And then what's my other thing? So current is the same throughout the whole circuit. It's a series circuit. So I won't need a phasor for current. No, what I need to find my current is basically use Ohm's law. And then what I'm going to do is I'm going to use my, right, Ohm's law. So we need to find my overall current. And that's why we have to find what our impedance factor is. So pretty much the next thing we would want to find out would what would be our impedance overall through the circuit, and use Ohm's law with the energy source to find out what my I total is. And then when we get I total, we could do a couple of things. We do the phasor diagram for voltage, because we know in a series circuit that voltage changes. We'll have 2 different voltage drops across our components here. And of course, with the capacitive element in there, right, we're going to be out of phase with each other. So we'll have to do some type of phasor, A, to find out what the magnitude is, and B, what the heck those angles are, right? Always the angles. So let's see how we do this. Shall we? No. So if we go through and plug, right, we use Pythagorean's theorem. We have our R value of the 1K. We have our X of C value of the 1.9K. So we would know that ZT would be equal to, and in this case, 1K squared plus a 1.9K squared. Combine those up, do the square root, and then overall you'll come out. And of course, I mean, yeah, these things are never nice and rounded for us or anything. So this one comes out to, it's pretty roughly like about a 2.2K. Okay, so now that's the magnitude of the phasor, right? So that's our overall impedance factor. And then when we want to find out the the angle, right? We're always going to use that angle of theta. And then we do that funny looking little arctangent one. And then we just have to have a ratio. And usually, and the ratio is always going to be what we're trying to develop here. So in this case, we're trying to develop impedance. So our two factors are going to be that X of C and that R. Okay, now we just have to remember, well, what the heck one goes into which spot? Well, the way they usually do it on doing the phase order, what you do is you have, see, I don't want to call it the imaginary number. You want to draw the unreal component, basically the reactive element. So in this case, our X of C goes over our real, which is the R, because the R has no phase change at all. Everybody see that? So your arctangent, so basically if you plugged it in your calculator, right, you would take your X of C, divide it by the R, hit your arctangent button, and it should give you some kind of angle. And always remember with these things, right, the angle tells us if it's more resistive circuit or if it's a more capacitive circuit. So anything less than 45 degrees brings it closer to the resistance factor. So then this circuit would be more resistive. If it's more than 45 degrees, right, swinging closer to 90, then that means the circuit's more capacitive. And yeah, I know, what's the point of that? But for right now, just suffice it to say, this is we do want to kind of know. We do use that later, why we would want to have a particular angle, and hopefully it'll start becoming a little more clear why we do go through that. Anyway, so enough. So if we go and plug through and we found out, well, let's see, what's my overall angle here? So we should come out to pretty close to about 60 point, excuse me, 63.3 degrees for our angle of theta. Remember theta? That's our little Greek letter. So many Greek letters we learn. So now we would have basically most of our factors for this circuit. We haven't gotten the current yet, but the current, I mean, that's going to be easy now, right? Because now we have an overall ZT and we have an overall voltage. So we go and just plugged into Ohm's law, right, where we have I is equal to E over R here. We could pretty much take our 25 volts here, and we're going to divide it by the overall impedance factor. So we have 2.2K, and with the K in the bottom, we know it's going to be somewhere in the milliamps here. So if we divide it out, it should come out to something about 11.2 milliamps. And then remember now, and I mean, just because we're dealing with reactive elements and stuff like that, we go through and plug in and we go, what? Okay, our current is the same throughout a series circuit. So we would have 11.2 milliamps on both of these, right? So then we could go ahead and figure out if we wanted to, we could just figure out our individual voltage drops. And then we would have, right, we would have what's your voltage drop of VR and what's your voltage drop of VC. And then that would be pretty much all of your unknowns for the series circuit. So really, I mean, it's just all in steps. And it's not, I mean, as far as the unknowns, it's still the same as what we were looking for before. I mean, we still follow the same steps. It's just because now with the AC signal in there, and since we have reactive elements and everything, well, what we have to do to get to these steps becomes a little interesting, if you will. All right. That was just a rehash. I won't dwell on that too long. Now, for the one everybody loves, apparently, the parallel elements, right? So, and again, I mean, in some ways, parallels can be harder, and in some ways, they can be easier. Oh, excuse me. There we go. to solve, really. I mean, all right. So if we were to look, we got our energy source, and our circuit, resistor in there, and then we throw a capacitor in there, resistor R, C value. Let's say he's 820. I'm just pulling these from the practice sheets I handed out, actually. And what the heck is that? 60 hertz. Yep. And that's 60 hertz. All right. So, what's the very first thing I want to find here? The very first thing, basically, in all of these, you always want to find out our missing element here, right? The X of C. And when we get more into inductors, we'll want to find the X of L. So we want to find out our reactive element first. So that's the high priority, okay? Because we can't do like things like Ohm's law and stuff like that if we don't have our impedance for the circuit. So we need to find that. That'll be pretty much our priority, and we have everything we need. You know, again, X of C is equal to 1 over 2 pi FC. All right. And so when in this case, what are our factors that we want to take a look at? So we take a look at 1 over the 6.28, right? And we multiply that out. What do we want? We want the frequency. And in this case, we have the 60 hertz. And then we do have a capacitor value of 2 micro. Yeah. Pretty much always, well, actually, that's one of the more larger ones. You're always going to deal with something really small with capacitive elements. They're usually measured micro down to nano, and then finally, like the little bitty, tiny, like circular ones. Those would be down in like the pico ranges. Use a lot in like radio or any kind of signal, low power signals and stuff like that. But anyway, so if we go through and plug in our math, right, da da da, da boom, 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 and at this point, I mean, that's just the thing we have to remember. Always remember, get this. Remember what the formula. This is one, I mean, I won't say you have to have it memorized, but it is handy because of how much you're going to use it, depending, going through these different circuits. That's the same with the inductor one. And they're fairly similar. So, I mean, you're always going to deal with 2 times pi. And anybody, I could point out, like, why the heck do we have to use 2 pi? And it's actually like a trick question, but that's the full cycle of the signal in radians. I mean, if we did it another way, I guess we could do it with, instead of using a pi value, we could do it with the degrees, but it would be a little complicated. But yeah, if we were to, anyway, yeah, I'll show you guys that on Thursday. Actually, we'll take a look at why the heck we do use pi and stuff like that. Anyhow, so we have our X to C value, and in this case, he's going to be about, what is that, about 1.3K ohms for this circuit. We plug that in through our math. So now we have an X to C value for our capacitive element. We have our R value. We have our voltage. We have our frequency. Now, what's the thing that's different about parallel networks, right, compared to the series? Well, in this case, we know since these things are in parallel right with the energy source, that voltage is going to be here and it's going to be here. So as far as that goes, I don't need to find the voltage. It's pretty much a given, right? Boom, boom. So no voltage figuring. What I do need to figure out is my currents. Because we know we have going in an overall current. Now we could say this is IS, current to the source, IT, total current, that kind of thing. But always remember, so if you do look at that, you do see a circuit says IS, and it's like, what the heck is that? Well, that would be the current at the source basically coming out of the energy source going into the circuit. But what we are interested in this case is what excuse me, can't speak today, our IR value and our IC value. So that's, remember, that's the unique thing about the parallel networks. So we do know the voltage is a given. So then we just have to go pop and pop. So there's two ways to do this, right? And it really depends on your knowns and unknowns you have for the circuit. I mean, the easiest way to do this, of course, is actually to go through and to use Ohm's law just to just to quickly figure out what our impedance are for these two. And then once we get what the two are, and then we can plug back and find out what our overall impedance are. But for right now, yeah, we're going to pretty much use Ohm's law. Okay, so we would have a phasor diagram for our current. So in this case, our IR, our IC, and I like I total, but if we used IS, that wouldn't be any big deal as well. So we find out our IC value. We go through and look, and it's like, okay, so what the heck do I know? Well, I know my voltage is 120 volts. So what's that formula? E over R's. And in this case, so IC, we'll be using that 1.3K value there and plug that in like so. And then we should come out, and of course the K in the bottom, we know this thing is going to be somewhere in a milliamp range. So if we plug it through, we should come up with something about, I don't know, I'm gonna keep it simple. We don't need like any great degree of accuracy. So about a 90.5 milliamp for our capacitive leg. So now let's find out what our resistive leg has. And again, so we have the 120 volts. And then we're going to divide that out by that nice little 820 down there. And if we plug that through, we should come up, we'll just round it out. We'll say he's about 146 milliamps. So now we have our two different currents for our legs here for parallel. So now comes the phasor part. So if we go back to the phasor diagram, now I have my real element, I have my reactive element. Now I need to find out my total element. So we just plug through and use Pythagorean's theorem. So really, from these circuits, the big thing, like, okay, what tells you when to use these phasor diagrams? And what it is the change-ups. So in parallel, current is my change-ups, so I'm going to have a current phasor. In the series, voltage is my change-up, so I'm going to have a voltage phasor. Just, I don't know, I'm rambling, I know, but it's just a high point to remember that, so that way that helps you remember. It's like, well, what phasor diagrams do I need? And then technically for both circuits, you would have like an impedance phasor. Excuse me. The parallel branch is a little trickier, and so we can do a couple of things and make our lives somewhat easier, I guess. And there are two ways we can do the overall impedance for this circuit. And there's the easy way, and then of course there's the more complicated way, I guess, if you will. So let us take a look and see. This thing looks like it's all backwards for some reason. My camera's, this is all goofy. Anyway, it is all backwards, isn't it? Oh. Well, I apologize. I'm gonna have to go through and play with these camera view things. I've never actually played with the camera view on Zoom. I can see now that this is like mirrored image. Anyway, well, hopefully we're able to follow this through. If I do this again, I'll make sure that this is a much better deal here. You guys are like my guinea pigs for like a live video demonstration. But anyway, so if we looked at our phasor and we wanted to develop what our IT is overall. So now in this case, really, to be honest with you, I would have two choices. I could figure out what my overall impedance is, and then just use Ohm's law to solve out my IT. But in this case, I already have both elements here, so we can just plug through and do Pythagorean theorem real quick and find out what my overall total is. And then we'll use that as an Ohm's law variant and find out what our impedance factor is. So if we did IT, in this case, right, we're going to do square root. What are we doing the square root of? That 90 and a half and that 146, all right? And do the square and the square, and then the square root, and then we should come out roughly about 172, so 172 milliamps, we'll say, overall in this circuit. So see, so what have we done so far? So we found our X of C value, we found our current in one leg, found our current in the other, and then we found our I total. So we've completed our phasor diagram for this particular circuit. So now it only leaves me with two things. And the easiest way to do this, now that I have I total and we have the voltage, and we want to find out what our overall Z is, then we can just use the Ohm's law real quickly and find out what our overall impedance is. And that's actually a much easier way to do it. Or there is a reciprocal style, and I don't know if I've shown you guys this or if the book was very clear, but the reciprocal style is very similar to what we had in DC, but in this case, we're going to go resistor, right? Resistor times reactance over resistor plus reactance. So we are able to use that method in case where, I don't know, you didn't have I total or something like that. So we could go through and plug it in like that. Of course, in this case, the easier way to go would be to use Ohm's law, right? And just figure out what our overall value is in this case. So we would be just what? Is it E over I, or is it E times I? What is it? No. Gotta mess with you. Gotta mess with you. Anyway, so you should come out. It should be pretty close if you're doing the math like with this. It would be 697 and a half for our overall impedance factor. And then and remember, whenever you finish these up, the one thing we haven't done yet, we have not figured out what our angle is. Let us know if this baby is more resistive or if it's more capacitive, right? So let us take a peek at that. What do we want to use for our step? Now, this one's a flip side of the other one, if you will. So we're still going to use, it's still going to be the arctangent, that funny looking guy. But in this case, at the other one, we had X of C over R. For parallel, we go R over X of C. And if we plug that through, we come up with about 31.7 degrees. So in this case, you can see that the angle is much closer to the resistance. So this particular circuit is much more resistive. So remember how parallel works, okay? What was the smallest element in this case? So we had the X of C, which was 1.3K, and the R was 820. And remember, in parallel, the smaller one always rides higher, if you will. I don't know if that helps any or anything. And that's just a simple approach. I mean, when we really get down to these circuits, what is our first step? Our first step is always finding out our reactive element. In this case, we're looking at the capacitors. So we always want to find out what our X of C is, okay? And in the case of inductors, we'll find out what our X of L. And then identify what are the unique things that you have about this particular circuit, right? And it does not change our overall element that we have. So parallel elements, the current is my change, right? Kirchhoff's current law. So if I have the current and that's what I have involved, then that means that's the one I have to do a lot of deduction with, because we know a voltage is going to be the same in these, right? And we go back to the series element ones. then we know, okay, what do I have? Well, current is a constant in this case, and voltage is my change up. So I have to do more figuring for what my voltage drops are for this in a series circuit. And that dictates what your phasor diagrams are. So in reality, really, what are we looking at? So we look at my current phasor, and then in series, we have a voltage phasor. Now you may or may not want to do the impedance phasor, okay? But they do apply in both cases. But again, just like going back into the DC thing, when we figure out our overall impedance, in this case, in a parallel, we use the reciprocal. And then because it's two different elements, we can't just merely add them together. And it's like as a series case, we can't just add them together because they're not existent on the same plane. They're out of phase with each other. And because of that, we have to do the Pythagorean theorem to figure out what that is. So that's just be the thing that I would do would be follow those steps. And then the very last thing, always find your angle. Find out what your angle of the deflection is. And then that way we could see is the circuit more reactive or is the circuit more resistive. I mean, it's rare that you find the exact one where you get, dead on 45 degrees, although those do exist. If you want a truly balanced circuit. Oh, this is making me crazy. I know, I'm mixing it up. Sorry. Ah, it's so scary. Take it away. But here, sure. So yeah, when we look at these, and I know it's not like the most perfect formula sheet in the world, but I think it does help a lot. Just the way, that it's laid out. And so, like in every quiz and every test, of course, yeah, it's all take home, so you guys use this anyway. But no, I would allow, you would allow a formula sheet to be part of the thing. Because I would never expect you to really truly memorize all this. I mean, if you use it long enough, like me, right, it starts to become secondhand. But I hope that helps. Because all right, let's go back here. Because yeah, I mean, we look at the parallel and the way they have the solutions. Yeah, see up there where the ZT is the reciprocal method. And this would be one way to solve ZT, or you do it the way I was showing you, just simply using Ohm's law. If you are unsure, you use the Ohm's law and you found out what your overall impedance was, and you wanted to do like a double check on it. Well, using the reciprocal method definitely will yield that. And that's the mystery to this thing. So go back here. See, so if you look at the series circuit, figuring out the angle, okay, we have the capacitive over the real element or the capacitive over the resistive element. But then you look in the parallel circuit, right? And you see that it's the resistive element over the capacitive. So they do a flip-flop as far as figuring out what the overall angle is here. But every time in these things, the very first thing we're always going to want us to find out is what the reactive capacity is of the element we're using, in this case, capacitor or, an inductor. So we need to find out like the X of C or the X of L value. That'd be the very first thing. So that way I have all my resistive elements all in a row, and then I can start doing some manipulation. And then when it comes down to it, we just have to remember the unique properties of these circuits. So, and I can't stress that enough. I mean, that takes away part of the mystery, I think. By doing the series, we're looking for voltage drops. By doing parallel, we're looking for current developments through the different legs. The voltage drop is going to be the same for each element through the parallel network. Where are we at here? Oh, excuse me. So yeah, when you go through this and look at, I mean, Ohm's law still always applies. If it's a straight then there is no angle to worry about, in each particular leg. Because down the resistive leg, how much angle of deflection is there? 0. And down the capacitive leg, how much angle is there? Negative 90. It goes straight down. Only in the combination do we come up with the strange angle. So as far as figuring out the elements by themselves, they have that straightforward application where this is this. The capacitors are dead 90 every time. but that would be the order I would do that in. Literally, go through, find out, all right, what's my reactive element, and then start finding my unknowns. And either series works that way, capacitors, and the reason we have to do this is because the energy source is in a constant state of flux. When you're in DC, there is no change with respect to time, okay? If I want to go out 2 seconds, what's my voltage level? Well, pretty much the same voltage level you had back at 0 seconds. But when we do it with AC analysis, going out 2 seconds, if the amplitude is still the same as it was at like 0.1 seconds, then something's seriously wrong with your circuit or with your energy source. But the AC signal is always in a constant state of flux. So we need to analyze that, how we go through that. And that's why we have things like RMS values and such. I mean, RMS values, and the reason we use that is basically how much like power you're using through a signal. Let's see here. I could show this now, but so if we looked at it, all right, if we look at it, yeah, I know. Yeah, this is my wonderful, perfect curves, aren't they? If we're dealing with RMS values and how much we're dealing with here. And that even gets us down to using like averages. So really, how much of this signal is getting used? So overall, we cannot use all of it. And that is because of the way of power and whatnot. I mean, the signal's in a constant state of change. And so when I go out to a halfway point, well, it's the same as the beginning. So I have 3 points where I do come to 0, 2 points where I come to high, and everything else in between isn't a change. And so if we were to look at like overall in the signal, how much of this signal do I actually use and draw it out? Actually, get something better here. If we were to draw it out, it's like, well, how much of the signal do you use? And unfortunately, you only use really about that much of it. If we were to draw like an overall like power consumption usage, basically, that would be how much you use of that thing. And that's why we do RMS values and average values and whatnot. And that's why I always felt that your electric meter should be basing you on that. I'm not getting into that fight, but anyway. It's just like the light bulb, right? Who still uses technology from 150 years ago? Well, your power company and your incandescent light bulb. Anyway, but I don't know. Does that help? Does that? I mean, I can start if you guys want. We can start maybe each week. We'll do a little half-hour practice session and go over the problems because we're still going to be going through inductors, and we're going to still be going through combinationals, right, where we'll be doing R, L, and C all together. So if you want, we can I'll set aside half an hour maybe, and then maybe I'll do that. I don't know, I have to think about that, but maybe we'll do it every Wednesday at the end of the lecture, and maybe take a little break or something, and then do like a half hour, and it doesn't mind, it's not a mandatory requirement.
That sounds fine.
Would that be something to work for him? I think, and would that help
Yeah,
you guys?
Yeah.
yeah. A little bit extra practice.
You know what I'm saying? And then maybe if you were, work out some of them beforehand and all that, that way if you, like whatever's stumping you or something like that, and then we can go in and look at it together and see, and it's like, okay, and try to help make this a little more sense. I mean, I'm gonna be honest with you, I don't expect you don't expect full understanding of this as we're going through it, right? I mean, really, let's get used to what we need to find, how we're applying this stuff, how we get the values and stuff like that. And then we start analyzing, well, what the heck do we need to know this for, kind of thing, you know what I mean? Like, okay, well, we do this because of this, but that comes after, I always think. But really, we got to learn how it's done, and then we learn like why it's done. But all right, so let's run with that, and then yeah, we'll meet tomorrow, and we'll have a lecture, and then Thursday we'll meet for lab, and then Thursday, if you want, we can go over some more stuff. If I can pull out a few more practice problems, I might have the first inductor set, the series inductor ones, so I'll probably hand those. In fact, that'll work out perfect. So I'll hand out the series inductor ones, and then we'll go over those. We'll let you play with those over the weekend, and then we'll go over those the following week. In fact, yeah, let's do that. I like this. So, and I know I'll work on the camera thing. I'll see if maybe school might have like a tripods type of little deal that I can use. I'm sure they probably have something like that. But yeah, I'll go through and I'll try to find that out, so we have a little better setup next time. I'm sorry. That's all I have. I have like my camera phone, and I got my PC camera. I've never really had a need for it anymore. But all right, gentlemen. Well, thanks for coming. I'm gonna, I'll post this. I don't know, probably in the dated. I don't know. I'll find a spot for it on Blackboard, and we'll keep these practice videos going, I guess. I hope it helped. If not, no, I'll make sure that the next time around we're more polished, and I'll be able to have better diagrams and stuff for you guys. I apologize, but all right. So yeah, let's do that, and then yeah, so we'll meet tomorrow for the lecture. And if you do have any questions or something like that, hey, bring them up now or bring them up tomorrow. I am always willing to go over stuff. You guys should know that by now. But do you have any questions? I mean, is everything cool? We're all good?
All good, sir.
All right.
Okay.
I'm going to hold you to this now. This was your moment. No. All right, gentlemen. Well, then let's do that. We'll, so I'll see you guys tomorrow morning for the lecture, and we'll go over that, more inductors. Big surprise, huh? And then yeah, and then we'll meet Thursday for lab and more inductors. But all right, so yeah, I'll see you guys tomorrow then. All right.
All right. Sounds fine. See you.
All right, gentlemen. You have a good one. You had trouble?
Take it easy.
Oh, I'm too old to get in trouble.